Okay, welcome to part 3 on our little sequence on sequences. This is going to call back a few things on part 1 as well. So we'll jump to a start first about geometric sequences, and then we'll cover a few things that I've missed out beforehand that I'm going to cover over now. So just as a recap, let's look at this question. So for a geometric sequence, we have a second term of 15 and a fourth term of 45. We should know how to start this now. We can write that as two equations. Remember, the power always lags one behind the term. To solve this, we label our terms and we divide our two equations against each other. That's going to give me AR cubed over AR equals 45 over 15. The A's cancel out and I'm left with R squared equals 9. Okay, this is a bit different now. And you're given a clue in the question, it's going to be different as well. And the question said work out what values of R it could be. And in maths papers, they never pluralize incorrectly. If they say values, they mean there's going to be more than one. So we should know if R squared equals 9, we have R could be plus or minus the square root of 9, which is 3. Note this is only true for even powers of R. This is not true for something like R cubed. That was only one solution. So we know R can either be plus or minus 3. Then says for each value of R, work out the corresponding value of A. So we grab this equation. We either have A times 3 equals 15, which gives me that A is 5. So if R is 3, I therefore have A equals 5. Or I've got A times minus 3 is 15, which means A is minus 5. So if R equals minus 3, then A equals minus 5. Then says work out the 10th term. That is going to be AR to the 9. And it says that with this sequence, those are going to be the same for each pair of values. So in each case, the minuses are going to cancel themselves out. Hence why I said work out the 10th term, not the possible value for the 10th term. That you can use either or use both. So you just type in 3 times 5 to the 9. Or minus 3 times minus 5 to 9. They give you the same answer. So what you do need to know when we cover here is the proof for the sum of the arithmetic and geometric sequences. So this we haven't seen yet, but we have already seen this sum here and we're going to prove it. A couple of ways you can do it. Another way to do the way in the book, because that's sometimes a bit nicer to write down. So what it wants us to do is prove this sum. And we're just going to list out all our terms first. We do the same thing for both sequences. So we have our first, second, third term. What I always do, I always write down the first 3 terms, then the last 3 terms. So our last term is A plus n minus 1d. So therefore our last but 1 term would be A plus n minus 2d. And A plus n minus 3d. Okay, so we kind of know the trick. We kind of know we have to add these together, and those pairs will always be the same. Okay, however, that's kind of quite hard to prove this way. The best way to prove it is to write the same sequence again, but this time we're going to write it backwards. So I'm going to write the exact same terms, except I'm writing everything in reverse. So that's now my first term. This is my second term. And this will be my third term. You will see why in a second. Okay, it's just a trick you have to remember for your exams. And again, has been examined quite a few times in the past few years. So I would recommend make sure you're okay with this. And throwing in the first 3 or the last 3 terms. We now have this. What we're now going to do is we're going to add these two sequences together. So if I add these together, I now have 2 lots of my sum equals, if I add these together, it's going to be 2a plus n minus 1d. If I add these 2 terms together, I've got 2a again. I'll do it in brackets. I've got n minus 2d here, and I have another d here. So one more d onto n minus 2 gives me n minus 1d. And it hopes where it's going. All these terms are going to be the same. They are all going to be 2a plus n minus 1d's. Okay. The question is, how many of these terms do we have? I actually know this. We were told right at the start we were summing n numbers together. So we have n lots of these terms. And if they're all the same, they will all equal n times 2a plus n minus 1d, because we have n lots of this term. Remember, that sequence is 2 lots of my sum, so therefore my sum will just be n over 2, or half n, 2a plus n minus 1d, as it should be. So hopefully that wasn't too bad. Again, that's something I expected to know. What we're going to look at today, I'm going to prove first as well, is the same sum but for a geometric sequence. And we're going to start the exact same way. I'm going to list out my sequence. So it's A, AR, AR squared. Again, I'll do first 3 and last 3. I know my last term is going to be AR to the n minus 1. So therefore before that it was AR to the n minus 2 and AR to the n minus 3. Now here the trick's a bit different. Okay, what we're going to do again is write another new sequence, but this new sequence is going to be the same. It's going to be RSN. Okay, I'm going to times everything by R. So it's going to look pretty similar, except each time now I have an extra power of R. Again, I'll do first 3 and last 3. Again, this is a lot harder to prove because that trick is not obvious, where the trick was kind of made sense for the first sequence. Okay, it gets slightly harder than this. What we're going to do is we're going to offset the sequence slightly. I'm going to drag it and shift it to here. Now what you should notice is that every term and the one beneath it are the same. Can we see that? Those terms are going to be exactly the same. That means I can take away these two terms. So if I do Sn minus Rsn, so basically doing the top line minus the bottom line, A, nothing has that, so that stays by itself. The 2 ARs went away, the 2 AR squareds went away, there'll be 2 AR cubes. Everything else will cancel out, except for this last term as well. Again, there was nothing to cancel out the AR to the N. And because I'm minus in this bottom row, that means I'm going to have a minus AR to the N here. I would say rewatch that a couple of times until it starts making sense. You basically minus the 2 rows and seeing what terms are left. Because this is left from the bottom row, that means it carried a negative sign, so we're minus in the bottom row from the top row. Okay. Now we have a lot more compressed thing. Okay. However, I just want Sn. I don't want 2 lots of Sn. So what we do to make that disappear only once, we take out a factor of Sn. So we have Sn over 1 minus R equals A over AR to the N. I then just divide by the 1 minus R, and we are done. In the formula booklet, they take out a factor of A. So it looks like that. So this is a fair bit harder just because it's not quite as obvious what we're doing. It's not as obvious where this comes from, but it's making sure it's in red one. But for the most part, you were given this formula booklet, you're just asked to use this one. Okay, we'll look at this later, by the way. It doesn't matter too much right now. Okay, let's see how we can use this. Okay, I'll just go through one example and I'll let you guys try the rest. So for question 1a, they want the sum of the first 8 terms. We just plug in what we know. We know that a equals 1. We know r equals 2, because each time I'm times the previous term by 2. And we have 8 terms. All you're going to do is plug that into this formula. So it will simply be Sn is going to be 1 brackets 1 minus 2 to the 8 all over 1 minus 2. Okay, plug it all out, and I think it's something like minus 255. 255. It is the same idea with the rest. Okay, they aren't too bad. Keep in mind for these questions, C, E, and F are a lot harder. Just don't know how many terms they are. Best way could be trying an error or just stuff with logs, but I'll let you puzzle for that yourselves. So give these questions a try, and then we'll move on. Okay, our next step, I said a minute ago, we had the sum to infinity, the other formula, which basically looked like that. This is where you add an infinite number of terms, such as this question here, where we have a half plus a quarter plus an eighth plus 16th plus a 32nd, on and on all the way to infinity, and we're going to work out what it equals. This one's quite a nice example. You can prove it just by looking at this simple diagram here. If you add all these numbers together, so on forever and ever and ever, you see we're getting closer and closer to 1. So we say the sum to infinity, by the time you reach infinity, this will actually equal 1. Okay, it's kind of a way to get your head round. It just basically means as you keep adding terms, you're going to get closer and closer and closer and closer and closer to 1. That's basically what sum to infinity means. So for that sequence, my first term was a half, and each time I was timesing by a half. So first term was a half, and each time to get from here to be times by a half. We're going to try and use this formula here to work out my sum to infinity. So let's just work out the sum of the first 1,000 terms so far. Okay, that's going to be a half, 1 minus a half to 1,000, all over 1 minus a half. Okay, and this half thousand is going to be a problem. Okay, let's put in the calculator and let's see what's wrong with that. Because we're doing a half times a half 1,000 times, that means each time this is going to halve its value. So by the time you do it 1,000 times, it is effectively 0. It's so small the calculator reads it as 0. So what it means here is when you have a sum to infinity and when it times by a number that's smaller than 1, this term here, this r to the n term, will always vanish. So let's write better notation than that. So the sum to infinity will be a 1 minus r to the power of infinity over 1 minus r. And this term will always vanish or go to 0. So we're just left with a over 1 minus r. Okay, you can't have to prove this, and it's a lot less likely than the previous proof. Just keep in mind roughly how it works. It's not too much really to get your head around. So we now have this formula for the sum to infinity. Let's apply it to my question over here. We had a half over 1 minus a half, so it's a half over a half, which just gives us 1. We're saying that's we got a second ago. So let's try it again using this question here. So we'll label things as always. My first term is a is a quarter, and I can see to get from here to here, you would times them by a quarter. If you know where it comes from, all you need to do is just do this divided by this, and that'll give you the common ratio. So a is a quarter, r is a quarter again, and then I'm just going to use the sum here. Okay, so sum to infinity is going to be a quarter over 1 minus a quarter, and I would just place in the calculator, and that comes out at giving you a third. Okay, next thing to know is when sequences will and won't converge. So converge basically means they will have an answer. They basically reach some sort of number when you do a sum to infinity. Now, sum to infinity formula only works if the number you're timesing by is between -1 and 1. Okay, that's basically because you need this term here to go to 0, and that will only happen if it's between -1 and 1. So we can look at these questions here and work out which sequences will converge. So for that, we need to work out the value of r. So for question 1, the value of r we can work out just by doing the second term divided by the first term. And here, that is upside down. And for the first question, I get a value of r being 5/6. Therefore, yes, it will converge. Let's look at the second term. we do the same thing. We have minus 7 over 3 over 7. That gives me an R value of minus a third. Again, that's between minus 1 and plus 1, so yes, it will converge. Question 3, we have 1/50th over 100th, and dividing those gives me an R value of 2. That is bigger than 1, so that will not convert. They'll basically get bigger and bigger and bigger, so never satisfying a number here. Question 4 is a slight trick question. If you work out the R value here, we get an R value of a half. However, you work out the R value here, you get an R value of 2/3, then 3/4, then 4/5. So this is not geometric. So we don't know right away if it will converge. Okay. It turns out this doesn't, but the test working at the R value only works for geometric sequences where that value of R is constant or always the same. Okay, can you just go through these questions on exercise 3E? Again, they'll be on the OneNote for you to have a look at if you need to. Okay, that is it for this video. Hope that was useful. And one more video on these questions to go.